In the world of fundamental physics, we've built cathedrals of science, machines like the Large Hadron Collider, with tunnels stretching 27 kilometers, that smash particles together near the speed of light to glimpse the universe's deepest secrets. For decades, the rule was simple. To see smaller things, you build a bigger machine. But what if that rule is about to be broken? What if we could shrink a machine the size of a city down to the size of a lab bench, or even the tip of your finger? A revolution is underway, a shift from brute force to finessed power, where lasers are teaching us how to shrink the giants of physics and place the power of discovery onto a tabletop. To understand this revolution, we first need to appreciate the empire it's disrupting. At its heart, a particle accelerator does exactly what its name suggests. It accelerates charged particles like electrons or protons to immense energies. The conventional way to do this, perfected over a century, is with something called a radio frequency, or RF cavity. Imagine a series of hollow copper chambers. You pump radio waves into them, creating an oscillating electric field. As a particle bunch enters, the field points forward, giving it a powerful kick. The particles then drift to the next chamber, just as its field switches to give another kick. It's like pushing a child on a swing. You apply force at just the right moment in the cycle to add more and more energy. To keep these zipping particles from flying off track, powerful magnets steer and focus them into a tight beam. The Large Hadron Collider is a circular accelerator, a synchrotron, that uses this principle. Its magnets bend the particles into a giant ring, allowing them to pass through the same RF cavities millions of times, gaining energy with each lap until two beams, traveling in opposite directions, are smashed into each other. These machines have been spectacular workhorses, discovering everything from quarks to the famous Higgs boson. But they've hit a wall. The problem is the material. There's a physical limit to how much electric field you can pump into a copper cavity before it breaks down, essentially a tiny lightning strike that damages the machine. This breakdown limit is about 100 million electron volts per meter. That sounds like a lot, but it means to reach an energy of 100 billion electron volts, you need an accelerator structure that's at least a kilometer long. To reach the trillions of electron volts at the LHC, particles have to circle the 27-kilometer ring hundreds of thousands of times a second. Physicists now dream of the next machine, one that could reach 100 trillion electron volts to explore physics beyond our current understanding. But the proposals, like the Future Circular Collider, envision a new tunnel nearly 100 kilometers long, with a price tag in the tens of billions of dollars. We are learning that simply scaling up our current technology is unsustainable. We can't just keep paving the planet with bigger and bigger accelerators. A new idea was needed. That new idea came in 1979 from two physicists at UCLA, Toshiki Tajima and John Dawson. They asked a radical question: what if the accelerator wasn't made of metal at all? What if it was made of plasma, a superheated gas of charged particles? They theorized that if you fired an incredibly intense, short-pulse laser into a plasma, it would create a moving wave of electric charge, like a motorboat creating a wake in water. This plasma wake field, they calculated, could generate electric fields 1,000 times stronger than any RF cavity. Electrons could get trapped in this wake and surf it, gaining massive amounts of energy in a very short distance. An accelerator that needed a kilometer of copper cavities could, in theory, be shrunk to just 1 meter. At the time, the lasers needed to do this didn't exist. But the idea was planted, waiting for technology to catch up. And it did, with the invention of a technique called chirped pulse amplification, which allows us to create mind-bogglingly powerful and short laser pulses. The era of Laser Wakefield Acceleration was born. Here's how it works. You start with a small puff of gas, say hydrogen, in a chamber just a few centimeters long. Then you fire a petawatt-class laser into it. A petawatt is a quadrillion watts. The laser pulse lasts only a few femtoseconds. That's a few quadrillionths of a second. The power is so concentrated, It instantly rips the electrons from the gas atoms, creating a plasma. The laser's intense electric field then acts like a snowplow, violently shoving the lightweight electrons out of its path. The heavier positive ions get left behind. This creates a bubble behind the laser pulse that's almost empty of electrons, but full of positive ions. The displaced electrons are intensely attracted back to this positive channel. They rush back in, overshoot, and create a powerful oscillating wave in their wake, the plasma wake field. The separation between the bunched-up electrons at the back of the bubble and the positive ions in front of them creates a colossal electric field. If you inject other electrons into the back of this bubble at just the right moment, they get trapped and propelled forward, surfing the wave at nearly the speed of light. The result is an acceleration gradient that can exceed 100 billion electron volts per meter. That's a 1,000-fold improvement, reducing a 2-mile accelerator down to the length of a few meters. For years, this was mostly theory and simulation. The turning point came in 2004. 3 separate teams in the US, the UK, and France all published landmark papers in the same issue of Nature. They had all managed to create high-quality, mono-energetic electron beams, meaning the accelerated electrons all had roughly the same energy. This dream beam proved the concept was viable for real-world applications and ignited a global research boom. Since then, the progress has been staggering. The Bella Center at Lawrence Berkeley National Lab has become a world leader. In 2014, they used their petawatt laser to accelerate electrons to 4.25 billion electron volts in just a 9-centimeter plasma tube. By 2019, they pushed that to 7.8 billion electron volts in a 20-centimeter tube. And just recently, they hit another milestone, a high-quality 10 billion electron volt beam in only 30 centimeters. But for all this spectacular progress, there are still major hurdles. To reach the energies needed for a future collider, you can't do it in one go. You'd need to chain hundreds or thousands of these plasma cells together, perfectly handing off the electron bunch from one stage to the next. This staging is an immense technical challenge, though the principle was first demonstrated in 2016. Then there's beam quality. It's good, but it's not yet as pristine as what conventional accelerators produce. And what about repetition? High-energy experiments need millions of particle bunches per second. The powerful lasers for this work historically fired about once per second. While that's improving, there's another problem: colliding electrons with their antimatter counterparts, positrons. The same plasma bubble that perfectly accelerates and focuses electrons does the exact opposite to positrons. It blows them apart. Solving this positron problem is a critical area of active research. While plasma systems are shrinking accelerators to the size of a room, a parallel, even more radical approach is shrinking them onto a silicon chip. This technology is called a Dielectric Laser Accelerator, or DLA. The idea is to use the same fabrication techniques that create the processors in your smartphone to mass-produce accelerators measured in millimeters. Instead of metal cavities or plasma, a DLA uses structures made from materials like glass or silicon. These materials can withstand laser-driven electric fields that are 10 to 100 times stronger than what metal can handle. Here's the concept. Using etching, you create a microscopic channel on a glass chip. The walls of this channel are patterned with incredibly precise nanoscale pillars or gratings. You then fire a laser at the chip. The light interacts with these patterns to create a near field, an electromagnetic field that's tightly confined to the surface. The pattern is designed so that this field oscillates in perfect sync, with particles traveling down the channel. So as an electron flies by, the laser-induced field is always pointing in the right direction to give it a tiny, powerful push. It's a continuous series of kicks, generating acceleration gradients that are, again, enormous. The entire accelerator is a transparent piece of glass, barely visible to the naked eye. The driving force behind this research is the Accelerator on a Chip International Program, or ACHIP, a collaboration between Stanford University, SLAC, and the University of Erlangen-Nuremberg in Germany. After a key proof of principle in 2013, the most significant milestone came in October 2023. The German and American teams published back-to-back papers in Nature, both having independently demonstrated, for the first time, a net acceleration of electrons in one of these nanophotonic structures. The German team, using a channel just half a millimeter long, boosted electrons from 28,000 electron volts to over 40,000. The energy gain is tiny, but the achievement is monumental. It was the first time anyone had successfully shown that a chip could both guide and accelerate electrons over a scalable distance. It proved the foundation of the technology is solid. Of course, the challenges here are also immense, just on a microscopic scale. The acceleration channel is only a few hundred nanometers wide. Getting a beam of electrons into that tiny opening without it crashing into the walls is extraordinarily difficult. And like with plasma, reaching high energies means staging thousands of these chips, each one powered by a laser timed with femtosecond precision. Finally, you have to build these chips with nanometer scale perfection. One tiny flaw in the pattern can ruin the whole process. So why go to all this trouble? Because shrinking accelerators from the size of cities to shoeboxes or chips could change everything. The most profound impact might be in medicine. Today, proton therapy is a superior form of cancer treatment. Unlike X-rays, protons deposit most of their energy directly in the tumor, sparing healthy tissue. This is critical for brain cancers or for treating children. But a proton therapy facility costs hundreds of millions of dollars and needs a building the size of a football field. A compact, laser-driven accelerator could dramatically reduce that size and cost, making it available in far more hospitals. The ultimate dream is an accelerator on an endoscope, a device so small it could be inserted into the body to irradiate a tumor from the inside. These compact machines could also produce short-lived medical isotopes on-site at hospitals for diagnostic scans, eliminating complex transport logistics. For scientists, it means bringing powerful tools into a standard university lab. One of the most exciting prospects is a tabletop X-ray free electron laser. These machines are like super strobe lights that let us watch chemical reactions happen in real time or map the structure of viruses. Today, there are only a handful of these kilometer-long, multi-billion-dollar facilities in the world. A Laser Wakefield Accelerator could power one that fits on a table, democratizing a revolutionary research tool. And what about the future of particle physics? While a full-scale laser-driven collider is still a distant dream, it offers a path to higher energies that might be cheaper and smaller than a 100-kilometer circular tunnel. The applications even extend to industry. Compact accelerators could be mounted on trucks to cure asphalt and build more durable roads, or used to 3D print high-performance metals for aerospace. They could power next-generation cargo scanners that can find illicit materials faster and more accurately. The journey from city-sized colliders to tabletop accelerators is a story of human ingenuity, of turning from brute force and sheer scale to finessed power and focused intensity. The colossal cathedrals of science like the LHC will continue to be our deepest probes into the fabric of reality. But this new generation of laser-driven machines is starting a different kind of revolution. They promise to put the extraordinary power of high-energy physics into the hands of more scientists, doctors, and innovators than ever before. The giants of physics are shrinking, and the future they will help us build will be forged not just from concrete and steel, but from plasma, silicon, and the undeniable power of light.